modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all three methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Hey folks, we will be getting started here in about a minute or so. At the top of the hour, we'll just give people another minute just to get registered and through the lobby there. For those of you on the line right now, I'll just make note. The session will be recorded and available for playback later on. If at any point you needed to drop off for whatever reason, don't worry, you'll be able to pick up on the content as needed. We will also reserve some time at the end of the session for a Q&A. You can see my colleague Landon is posting in the chat box right now. So if you do have any questions or if there are any issues that you need help with, please feel free to make use of that chat box, and we'll help you out accordingly. We'll also be posting various links and content resources into the chat as the session progresses. So if you definitely feel free to take a look at any of that as it pertains to interests. All right, so top of the hour now. We'll get started here. So let me. All right. So good day, folks. Officially welcome to the first C-Therm webinar of the year. Hope everyone is having a good new year. Today we are taking a look at one of our more popular application webinars of 2023, taking a look at some of the content on phase change materials and really the importance of thermal conductivity in these applications. So we'll be going over quite a few different areas of application for PCMs, such as thermal energy storage, biomedical, thermal management of batteries, and the sort. So that will kind of set the tone for our session here today. Let's jump into it. So before we get into the main body of the PCM webinar, I will just give a little bit of a background on us here at C-Therm, for those who may be new to us, or this is kind of the first time you've been a part of one of these webinars. So really here at C-Therm, our purpose statement, what we do, our goal is simplifying thermal conductivity for the testing for the materials of tomorrow. We do this through the advancement of various methods for thermal conductivity characterization, which we'll be talking about here today. So the main system that we'll be focusing on is Trident. You can see here Trident is a modular platform. This was developed with multiple methods for thermal conductivity characterization. Each one of these different options, of course, plays with different sample types, different sample formats, testing conditions, things of this nature. Today, primarily with PCMs, we will be focusing a lot on the MTPS, or the Modified Transient Plane Source, the sensor right here. But of course, happy to provide context or information on others if there were questions. So Trident being a modular platform, really the reason for its development and the idea behind it, you kind of draw some relevancy to this quote by Abraham Maslow. It says, "When all you have is a hammer, everything looks like a nail." And this touches to the point of, if you're taking a really good method for thermal conductivity, whatever that may be, but applying it in an area or on a material that it really wasn't designed for, you're not really setting yourself up for success. So with the Trident having multiple options, really taking that toolbox approach, allowing you to pick the best tool for the task at hand. Now, that being said, when looking at one method, especially if you're new to the area, that can be quite a lot. But taking a look at three or other options out there can be a little confusing, especially again if you're not familiar heavily with thermal analysis. So we do have this is a free to download method selection guide, which covers all of the methods that we offer here on Trident, as well as other industry offerings, different methods that are out there. So definitely feel free to download that, take a look. Again, all of these links, different content pieces that are being discussed here today, you'll see some links in the chat box being posted by us at C-Therm here. So definitely feel free to take a look at those. And if as we're going through this, if something sparks your interest and really you could see some benefit, or maybe you would like to really just learn a little bit more, more of a one-on-one, we do offer technical consultations, so you can book some time with us to talk about your testing application needs in particular. We can even show you a live system demonstration on some representative samples. Definitely, happy to accommodate as there is interest. Also, maybe you have a good idea of what you're looking for. You just want to know some pricing. We can also provide a quick quote to you as well. And closing out the kind of the intro portion here, I wanted to end with a client testimonial in the PCM space. We always like to talk about what our, relay what our clients have to say about us. This one here is from Dr. Samuel Plunkett, the Director of Battery Technology at Beam Global, kind of taking a note that they were able to look at the thermal conductivity quickly of their phase change composite materials. They were doing applications in lithium-ion battery packs. He mentioned it was really nice that they didn't require extensive sample preparation, no coding. The price was appealing, and it was easy to use compared to traditional methods like the LFA, laser flash analysis, kind of noting it was a triple win. They use it weekly in characterizing their materials. So, really nice to hear stuff like that. And again, if you want to hear more about what our clients have to say, definitely take a look at the link provided in the chat. So today's session will be, 95% focused on thermal conductivity, and that's what we're going to take a look at. But I do just want to make note that we also work with Rigaku. They are a company that specializes in thermal analysis, primarily DSC, STA, TMA instruments. And when we're talking about phase change materials, things like CP, heat capacity, do play an important role. Again, it won't be the main focus, but I do have a little bit of an outro content piece on heat capacity analysis with some of the Rigaku systems. And they have a very cool tool here within their software, in their system, the sample observation. So you'll actually be able to not only see the data collected, but you can see what is happening to the sample live as it's occurring. And I have an example of that we'll take a look at near the end if CP was potentially of interest to you guys. All right, so to the main topic, really looking at thermal conductivity in phase change materials. And as I mentioned, we're going to be looking at quite a few different application spaces here today. But I'll first start with just a very high-level background on PCMs. This might be very common knowledge for some, but just to make sure if there were anyone new to the field, just to kind of go over this. So really a phase change material, kind of it's in the name, but it's a sample type of material that is going to undergo a transition based on the change in temperature in the system. So it'll generally follow this track, solid state. You introduce temperature into the system. The PCM begins to absorb that thermal input, melts, goes into the liquid state, and then the reverse can happen as well. So, quite straightforward from that regard. But what's really interesting, and where a lot of these applications really lean on some of the characteristics of the PCM, is what's actually happening with respect to the system temperature during either the melting or the solidification of the sample as it's occurring. And this is really where I'll call it the magic happens. It's really looking at the sensible versus the latent heat and how that can be harnessed for these various application needs. So really, describes the exchange of heat under specific conditions with respect to their influence on a material or thermodynamic system. So the idea here is that if your sample, we were, increasing the temperature of the system and the sample is increasing, we see that, it's in the solid state, it's still in the solid state, but you're increasing the amount of energy into the system. We see this is going. Then once it hits that phase change temperature, what's going to happen is it's going to begin to melt. But as we're still introducing more and more energy, more and more heat being stored in the system, the temperature of the material, of these phase change materials, are remaining constant, and that's the latent heat effect. And then once it goes fully through, of course, it will enter to a fully liquid state and return to sensible. But these two different forms of temperature and heat are really what's going to be driving a lot of the conversation. So again, your sensible heat, this is thermal energy exchange, which results in a change in temperature. It can be sensed. That's kind of where the name comes from there. You can measure that directly, see that temperature change occurring. Whereas the latent heat, also known as heat of transformation, this is more of that invisible or hidden heat exchange that occurs without a change in temperature. So this is, again, just kind of setting up the basis for what we'll be chatting about here today in further detail. Now, common challenges with PCMs. These three on screen here are generally what you'll see referenced most often in different publications, different applications. There are, of course, application-specific challenges that need to be addressed, but at a high level, we can break this down into the following three: the limited available latent heat, liquid phase leakage during transition, and generally low thermal conductivity. So what each one of these really do, they affect things a little bit in a different way. So your limited available latent heat, this, it limits you on how much energy absorption and storage is potential within that material or being used in the system. Liquid phase leakage, this limits energy absorption. That's a typo there, sorry. This is actually an issue with regarding to the cycling. So as you go from solid to liquid state, you can have some issues there. And then low thermal conductivity. So this impairs the heat transfer efficiency of the stored system. So once that energy is stored, it needs to be transferred to be able to be used for whatever purpose that is. But the efficiency of that is an issue when you have low thermal conductivity. And this is the one that we're going to be, again, kind of taking a look at here today. So what is thermal conductivity? Again, might be some basic review for many, but if you're new to the topic, thermal conductivity essentially describes a material's ability to conduct heat. This is an intrinsic material property independent of material shape or size. We'll be referring to the units of thermal conductivity, watts per meter Kelvin, standard SI units. And you can see where this is kind of built up from. You have a thermal energy input, watts, traveling through a given thickness of material, noted here for M, across a temperature difference. So this is kind of your standard breakdown, but we're going to be going into this in further detail. Again, really looking at areas of addressing low thermal conductivity, what issues those are causing, and how they're over. So as I mentioned at the top of the session, primarily in today's webinar, we'll be looking at the modified transient plane source, MTPS. So I just want to give a few quick points about the MTPS in particular as it relates to either your setup, some sample consideration, things of that nature. First off, it's a single-sided sensor design. This has some really nice functional considerations with respect to how you set your material up, the size and the amount of sample that's needed. Thermal conductivity and effusivity, these are the two properties that are measured and reported out from your test. We'll also be covering conductivity and effusivity. We have examples of both of those in today's session. Fast measurement times. So transient techniques, which is what the MTPS is a transient will always be faster than your traditional steady state options, just inherent to the fundamentals of the measurement itself. But even within the transient space, the MTPS does carry some of the fastest test times. Again, 1 to 3 seconds. It's that is on the very low end. There's guard ring technology. Wanted to make a note of this as it has bearing on the measurement directionality. In some cases, if you're dealing with anisotropic materials, There's directional dependencies there that could have some importance with the method that you employ. And with the MTPS, you have a controlled directionality based on that guard ring. There's high temperature, high pressure capabilities, testing in different saturated and humidity environments. There's a lot of options therein. But the big point here, and I want to mention this final one, is it's a very versatile sample type that you can test. So solids, liquids, powders, pastes. And this is a key component here for us today because PCMs will be taking a look at those in the solid as well as the liquid state. So it's really nice to have one method that can really handle both of those material types, to keep things consistent, especially throughout your testing. So from a principles of operation standpoint, again, won't go too deep into the weeds here today, but essentially how the measurement works is there is a heating element on the top side of the sensor, you can see here. This is what's going to, of course, impart that thermal input to your material for the test. So as the sensor coil heats up, delivers that thermal input, the sensor is simultaneously monitoring the change in temperature that occurs as a function of time. Now, what that is going to do for you is, what you'll see, materials that are generally lower in conductivity, something more insulative in nature, you'll see a steeper rise in temperature in the test compared to something more conductive like a metal, it'll be much flatter. But it's based on the rate of change that's observed during the measurement. This is where your thermal properties are determined from. And the nice thing with the MTPS is that it's a calibrated technique. So all of the data analysis and really all of the parameters that are used for the setting up of the measurement, these are all handled automatically by the software. I'll leave it there, but if you wanted to go into this in further detail, again, definitely happy to go into more of a one-on-one discussion with you folks if this is something you're interested in pursuing. But wanting to jump in now into some of these, application areas. The first one we're going to take a look at is thermal energy storage. So thermal energy storage, or TES, these are technologies that allow excess energy, so that thermal energy in your system, to be stored in some medium and then used at a later time for heating or cooling applications, depending on what you're working with. So again, there are different thermal energy storage systems. Some will work with the sensible heat storage, the latent heat storage, which is a lot of what we'll be kind of focusing on. There's also thermochemical heat storage, that you can kind of go down that rabbit hole, but we'll be taking primarily a look at the latent heat storage systems. So this application highlight here, this first one, is thermal energy storage in building materials. So it's employing the PCM technology in a way that can help improve on the materials that are being used to construct houses, buildings, offices, things of this sort. So we're taking a look here at a paper. This was published, I believe it was a year or two ago, but the development of shape-stabilized phase change materials utilizing natural and industrial byproducts for thermal energy storage in buildings. So this is some work coming out of Saudi Arabia. They are, a few different groups involved that use the MTPS method for their study. So I'll kind of break down some of the components of what they were doing, what they were looking to show, but also focusing in specifically on the thermal conductivity data that they obtained and really what it tells, or what the story told about the systems that they were working with. So shape-stabilized PCMs. Mentioning right at the beginning, one of the main drawbacks of PCMs being used are limited available latent heat, cycling issues, and low conductivity. And in this paper, they mentioned all three of those. Of course, it's pretty common to see those as kind of in the beginning of the paper, challenges that are going to be addressed. But one of the things I really dove in on is the problem regarding the structural integrity on cycling and really focusing in on that phase change leakage, with some considerations on thermal conductivity as well. So their solution here was to add to load their PCM onto a physical support to maintain structural integrity during the application. So what they were doing in this study, they looked at a few different support systems. There was an oil ash, which would be denoted as OA, scoria, SC, and expanded perlite, EXP. So 3 different systems used to stabilize a polyethylene glycol PEG-based PCM. So let's take a look at some of their findings. So you can see here, just maybe to get an idea of the differences between those 3 support systems, some SEM imaging. And you can see, between the oil ash, scoria, and the expanded perlite, 3 very different looking systems. So of course, how that PCM is going to integrate and load into the overall structure. 3 very different approaches to that. But each one of these, of course, has a certain effect. If you're adding something to the polyethylene glycol, it's going to inherently change not only the mechanical and structural properties, but the material properties such as thermal conductivity as well. So taking a look at some of their initial results, they found that the thermal conductivity, comparing everything to their control, just the blank PEG, we can see here that the oil ash and the scoria thermal conductivity did increase quite significantly compared to their control, over double and almost 4x here on the oil ash. But what they noticed is, although it had a significant increase in conductivity, it still suffered quite heavily from that liquid phase leakage. Now, conversely, their findings on the EXP PCM, they saw actually a decrease in thermal conductivity. So this must have had some insulative behavior introduced into their system, compared to their control, which isn't great. But this did have excellent cycling integrity. So, it kind of fixed one problem, didn't address the other. So what they decided to do is, because even though these 2 really boosted conductivity to a significant degree, the cycling was just something they couldn't manage with those 2 options. So they began an investigation further into this, looking at the incorporation of a conductive filler to help improve on the thermal behavior of the EXPP system while hoping to maintain that cycling integrity. So here are some sample images at different temperatures of some of these samples, and you can see here the filler, or the additive conductive filler that they were using, was a CNT at different weight percentages. But you can see, like, the samples at room temp, all fairly solid. Now at temperature, you can see some of the structural change that occurred here. And of course, this one just completely melted, whereas these 2 look quite strong there at that ADC point. So the thermal conductivity results of these filled systems. So, generally, as you might expect, the introduction of that conductive filler did boost performance. So we saw, especially compared to that control, and it's good that it wasn't decreasing further. Now we do see a net increase in thermal conductivity, and it did maintain the cycling benefits that were already noted for EXP. So although these thermal conductivity values at the 0.5 and 1% aren't, they're still a little bit kind of lower than the oil ash, which was much higher. It did achieve a net improvement compared to the base and address the cycling issue. So they were able to overcome those 2 challenges. So the conclusions that they drew from a thermal and physiochemical perspective, the 0.5% CNT loaded phase change composite exhibited the best overall performance. They saw excellent thermal cycle behavior within the sample. You can kind of see some SEM images that were taken there as well. And like I mentioned, even though these 2 options did have a higher base conductivity, those leakage issues were essentially rendering them non-viable for this application. So EXP was ideal for the leak negation, but required the conductive additive to really be employed properly for thermal energy storage applications. All right, so that was our first application focus. We'll pivot now into kind of a slightly different area, PCMs, but for use in EV thermal management. So if you've been following EVs a lot of what's going into there. One of the the big scare words that everyone doesn't want to hear pop up is thermal runaway. But it is something that it's a very serious consideration in the design and the development of these systems. And of course, it can be very dangerous if it isn't handled properly. So again, if you're unfamiliar, thermal runaway is essentially a form of a positive feedback loop where heat is introduced into your system, increases the exothermic or introduces an exothermic reaction, and then that further increases the rate of that reaction, increasing heat, and of course it goes through that cycle. Now, if there is no form for heat to escape and slow that reaction down, that's where it starts to spiral and enter into a destructive event, which of course will destroy the system. There's financial considerations, liability and safety, a lot of things going on there. So, you can get thermal runaway associated with different chemical and electrical interactions, different systems, depending on what we're looking at. But overall, generally speaking, you can mitigate the risk of thermal runaway through the use of a thermal management system, or TMS. And these thermal management systems are generally employed using things like thermal interface materials, or TIMs, within the build and the materials of the system. So I do just want to speak to thermal interface materials because this is really where the PCMs will come into play. But TIMs act as an intermediate to improve transfer between that heat generating systems, whether it's the battery pack, the electronic components, what have you, and the heat dissipating device, so your sinks or air cooling fans, things of that sort. So there are a range of different TIMs that are out there, a lot of different options for a lot of different application spaces. But PCMs, phase change materials, are considered a thermal interface material in this space. Now, I will note that phase change materials aren't as readily abundant when we do look at a lot of the literature on battery storage. But in recent years, actually, there has been quite a bit of work done on this using phase change materials, and I expect to see some more work coming in the future as well. So this application highlights specifically looking at battery thermal management systems where PCMs were employed. So this is a paper that we're looking at, again, from a few years back, but out of Canada and the US. So again, another joint work here titled Electrochemical Thermal Evaluation of an Integrated Thermal Management System for Lithium-Ion Battery Modules. So PCMs for thermal management challenges. Again, you'll see some very similar points here, especially for thermal runaway, kind of managing that. The aggressive operation that is generally seen in some battery systems, alone, the PCM isn't really going to handle that. Unfavorable thermal inertia, again, limited available latent heat, low thermal conductivity. But all in all, their proposed solution in this study, and you'll see this as a commonality as well, is to enhance the effective thermal conductivity using a filler. And in this case, they were looking at a graphite material. So looking at some of the results here, we can see two very distinct things happening. So at the lower temperature, before the material goes into the melt state, so which you can kind of see happening here at 50 degrees or so, when we look at just the baselining 30, 40, 50, the pure wax, the pure PCM, of course, is the lowest. And then we see at the 5 and then 10% loading, a much higher thermal conductivity is observed. Now, what's interesting, as they noted in this, is the phase transition as it's occurring when it becomes a liquid state. A lot of that differentiation that they saw somewhat disappeared. So within their system here, there could have been a very large impact on the overall structure that was formed between the PCM and the conductive filler, really having a large impact on those net changes. And of course, when we go into that liquid state, I believe they didn't have any bound control on the structure of these. And going fully liquid, they basically lost that net difference. You can see very minimal differences between those sample types at different loading levels. But this really does, again, it illustrates the point of, if you are working with a system that you want to be able to measure both liquid and solid samples, the MTPS is a great option there. You can see the setup is very similar. That you put your sample in on the top side. Really, the only difference for liquids is, as you can see, there's a containment vessel or a liquid cell, which you can either pour a liquid into or put a solid in, run it through a temperature profile, and have that melted. So there are a few different options there, but again, keeping everything under one roof, let's say, from the measurement perspective, can have some really nice uses with respect to the applicability for PCMs. So their conclusions that they draw, they actually use some of the thermal conductivity input to do some simulation studies. We'll see that quite often with groups that we work with as well. But the thermal conductivity really being used to help understand how much heat is going to build up based on the different properties. So, the high level summary is the thermal conductivity did increase with increasing graphite content. The thermal performance before and after the cycling transition, of course, were quite different. But at the end, their kind of final remarks were the PCM can maintain a temperature about 1 to 2 degrees lower compared to the pure paraffin at the different weight loadings, respectively. And a couple degrees can be quite significant if you are dealing with battery systems, especially with regards to the uniformity of the pack and things of that sort. All right, the next one that we're looking at, so we're kind of jumping into a thermal energy storage PCMs, but for biomedical applications, so kind of coming back to the TES side of things, but in kind of a different view. So this was a paper published last year, a group in India using the MTPS, and I just wanted to highlight this. Again, you'll see some very, very similar, topics being discussed as challenges or things that needed to be overcome. So biomedical devices will carry very similar things to the standard electronic systems, but of course there's going to be an added emphasis on biocompatibility, and safety as it's being employed for, contact with the human body or internally. So one of the additional things that they also noted as something to consider was the melting temperature range, because they were working, of course, in a human system. That was the idea for the kind of the application. So a battery pack versus a building versus a human body, those temperature ranges are quite different. So you do have to pick PCMs or pick materials that really conform to the melting temperatures that you're looking for. But again, you'll see some similar aspects where the innate material limitations, low K, things of this sort, are something they needed to work on, and the use of fillers often employed to tailor that performance. So they were looking at what is called an OM35 PCM with a silicon carbide filler. They selected this PCM primarily for the melting temperature range and recrystallization kind of around that 35, 37 degrees Celsius point. And the silicon carbide is just simply a readily available high thermally conductive additive. So they worked with this, and you can kind of see some images, a little bit blurry there, but the images of how these samples were produced and the final pellet that was used for testing. And kind of just, quickly looking at the thermal conductivity results that were obtained between the OM35, as you would expect, the one that had the 3% weight loading of silicon carbide did introduce an increase in thermal conductivity, about 2x compared to their base control. So, like I said, when we're looking at these different applications, there will be a lot of similarities and trends that are observed and things that are done to overcome these challenges. But really what is the main challenge or the main considerations are highly dependent on where they're being used. And of course, with a topic like PCMs, they can be, quite vast and diverse, and depending on what you're looking at. All right, so going into the fourth and the final application focus is on thermal performance of textiles. So at C-Therm, we do a lot of work with textile characterization with respect to the warm feel, cool touch. This has a lot of bearing in R&D development, but also QA, product, raw material sourcing and things of this sort. The idea behind the what we call warm feel, cool touch it's related to the thermal effusivity of the sample. So something that is warmer feeling will have a much lower thermal effusivity compared to something more cool to the touch, which is of course higher. But you can see some general examples here, like, a fleece or a wool. These are on the lower end. These are, materials often used in, the fall, winter wear, where you want to feel warmer, cozier, kind of combating the cold temperatures and maybe even snow, depending on where you're living. But, of course, if you're looking to develop activewear, things that athletes or trainers are going to be using, you don't want to overheat, so you want to have more of a cool touch sensation. Really, the perception behind that as well can also be important. So this is where the effusivity characterization can come into play. So as I mentioned, thermal effusivity, kind of see denoted here by E. It's also referred to as thermal inertia in some literature. It's defined as a material's ability to exchange heat with another body that it's in contact with. The units here, watts second to the 1/2 per meter squared Kelvin. And thermal effusivity is related to thermal conductivity. So understanding conductivity, effusivity, and other properties such as heat capacity and density, these, you can, measuring of some of these, you can kind of understand or calculate others as well. But they are all related in that sense. One of the other applications that we've seen is really the perception related to the temperature change that occurs between the interfaces upon touch. So again, like if you take the human hand and you touch a material, different materials will of course feel quite differently. So, some extremes being something quite low in effusivity, something insulative, compared to something like on the extreme other end, like a metal. Those two samples, even if they're left out at room temperature, so they're technically both the same temperature, let's say 25 degrees, 23 degrees Celsius. If you touch both of those, the metal is going to feel extremely colder, but it's related to what's actually occurring at the interface upon contact. So wanted to take a look at a little application highlight on fabric cooling treatments here using PCM. So this is some work from quite a few years back, but it really helps illustrate the point. So taking a look at the PCMs being employed as a form of a cooling system within, so this was being applied on things like mattresses, different clothing, different fibers. This company, they, what they came to us with was the idea that their treatments, if you could get someone in front to touch some samples, like actually feel the material, so tested or handle an untreated versus a treated material, you could really pick up on those differences. It's subjective, of course, but there was definitely no denying there was some amount of cooler feeling when touching those treated samples. But of course, if you're not able to get in front of someone to do that demonstration, the lockdown that happened, restrictions on travel, and even now, like people not traveling as much, being much more virtual, they needed a way to help quantify that performance in more of a systematic way rather than being rather subjective. So this is where the thermal effusivity comes into play. So there was a few samples that were tested here. There was first an intralock fabric, and secondly, a non-woven high loft. So these are two different materials, but we can see within each one of their test sets, looking at the untreated versus the treated sample, there is this net increase in the measured thermal effusivity between the two. So clearly that coating, that PCM treatment is boosting that effective measurement, and again, correlating to a higher effusivity, being more cool to the touch. So, now they can, of course, work with data like this to provide more quantifiable data results and context to people that are interested. And again, we've seen within the textile space, cooling is a really big area of interest for many folks. Again, the activewear industry, but also mattresses and bedding companies. That's the I'd say quite a bit of work is being done in that space with respect to some of the topics mentioned here. Okay, so kind of finished some real specific application points, but I did want to touch on the component of the filler, because as we looked at pretty much all of those Most of those application focuses did have fillers being incorporated in some way or the other. Now, there are some assumptions that are typically made, and often they hold true, but I just want to go through some of these. So the filler load, and if you increase the amount of filler, you should result in a higher thermal conductivity value. There's also considerations on things like the aspect ratio, or the type or shape of the filler. A higher aspect ratio should also generally lead to a higher thermal conductivity. But this last point here, this is something that I want to highlight, is the filler organization and distribution. So a better organized system will typically have a higher thermal conductivity based on the heat transfer paths that are generated. And there's an example coming up that I really want to highlight because it really demonstrates why this is important. So we've been working with quantifying the mapping or the thermal characterization of filled systems for a while now. And this is just a quick example. This was just a standard polymer that was filled with a conductive material. But just looking at this sample, we can see very non-uniform in its distribution. That's just by looking at it, you can tell that. But what you can actually do with the MTPS, because it's a single-sided technique, again, very small active area, very quick measurement, we can kind of spot test multiple areas across a material. And then what we will get, of course, is the resulting thermal conductivity. And as you would expect in this example, we're seeing some very large deviation from spot to spot. But if we go into that further, it really does correlate back to the sample in question. So for example here, this area here, about 0.347 watts per meter Kelvin, this was the lowest measurement taken on the sample, test location number 2. As we can see, it is one of the areas with essentially the smallest amount of filler present. And if you contrast that with the top right spot here, about 0.968 watts per meter Kelvin, spot number 3, very clearly over the area that is much more densely filled. So, with that idea, it's very clearly correlated. And, again, for a sample like this, you wouldn't really even have to test. You would just look at it and say, yeah, whatever happened in the production here, it's not great. Probably get, scrapped, reformulate, what have you. But there are cases where materials are going to simply be opaque in nature, or the filler distribution, dispersion within the sample isn't as visibly detectable. So in cases like this, whether it's in the R&D during formulation or again later on down the line for QA/QC, the MTPS does have a lot of bearing here on being able to pick up on those differences that may be occurring within the sample. And this is the paper I wanted to highlight for this aspect. Again, it's not strictly a PCM, but it really illustrates the dispersion organizational importance and some of those assumptions that are made with regards to the thermal conductivity increases based on filler. So this is some work out of China. This is also published using the MTPS. Excuse me. They're looking at the preparation of a graphene-based hydrogel thermal interface material, noting excellent heat dissipation and mechanical properties. And again, not purely a PCM, but the reason I wanted to show it is just for this point right here. So when we looked at their thermal conductivity results, we saw a very interesting aspect. As they increased the graphene dosage, it didn't increase continuously with the thermal conductivity. We actually saw a net decrease in thermal conductivity as more graphene was being introduced. That assumption where more filler will simply result in a higher value just didn't hold true. And what they were attributing this to is the fact that even though the higher filler was introducing more into the system, there was a certain amount, there's a threshold that was clearly met right around here that made it so how the filler was dispersed within the system was very different. So even though this point here had a much lower loading compared to one of the higher ones, the dispersion that was able to occur in their process was visibly looking at this very, very good. As you increase that further, that dispersion, something was going on, causing it to agglomerate, chunk together, what have you, but ultimately resulted in a detrimental effect to the thermal conductivity. So just wanted to kind of close out with that, as it really illustrates why quantifying your filler organization within the sample can be very important. and making sure you are getting the best possible output for your intended application. So we're getting close to the end here, but as I mentioned, I do want to just kind of highlight a quick PCM application from our colleagues or partners at Rigaku. They did some work here on the thermal behavior of paraffin wax by sample observation DSC. So, the paraffin wax PCM. But again, I just want to show you this. There's actually a video I'm going to play here looking at the sample observation using their Rigaku system. And again, it's just a really neat thing to see. I can get the pointer here to stop. There we go. All right, so we can see here, and it's really interesting because sometimes when you're looking at these curves, those very minor events, or is it actually something occurring within the sample? Was it noise? Is it important? So sometimes it's hard to tell, but with the image here, with the video, we can see everything occurring as it relates to those peaks. These can be overlaid, you can play them back. And now it's going from that upper temperature point, cooling back down. See that recrystallization there. So again, it's just, I'll stop that there, but it's just a really nice way to show what's going on within the data. So again, this was a fairly simple example, but of course, if you had a multi-component system, a little more complex in nature, something like this could really help you understand what's going on and, not mistakenly dismiss something for being noise when it's an actual event. All right, so with that, I'd like to say thank you for those who are in attendance here today. Really appreciate you joining. Hope you got some good information out of today's session. A few housekeeping items I just want to wrap up before we go into the official Q&A. If you were interested, we do have a range of resources available on our website, past webinars, different tech libraries containing, application papers. Those are all available for you guys, so definitely feel free to take a look there. Upcoming events. So we are beginning our year of conferences and travel. One of the first ones we will be attending is the IME West. This is going to be held February 6th to 8th in Anaheim, California there. So, if you're in the area, you'll be stopping in. Definitely feel free to connect with us. I'm happy to discuss, again, talk about your application or your testing needs in person. Maybe travel isn't your cup of tea right now. You're just busy, not going to be out and about. We do have upcoming online webinars, again, still be metered out over the next few weeks, few months. We'll generally keep a cadence of about 1 to 2 a month for you to take part in. The topic of the next one that's happening at the end of January is thermal mapping for improved modeling processes. So really taking a look at what we kind of finished on there with respect to the importance of mapping filler behavior. And we actually have a special guest, Sean Duffy, who is a polymer development scientist from Synergy. So he will be joining as a guest speaker to talk about how the thermal mapping is important and how they're using the system to help quantify that. So yeah, give us a follow on LinkedIn if you want to stay tuned for the the recent blog posts, upcoming events, webinars. We always post to LinkedIn first. So if you want to keep up to date with us, definitely feel free to give us a follow. And with that, we will now conclude the formal recorded session here today. Again, just one more